All right.
Okay, we have a quorum. Welcome to the thesis defense for Andrew Rouditchenko. The committee is Bill Freeman and Yoon Kim sitting right here. Just a reminder to everybody, Andrew will present his work. This is a public seminar, so first hour or so, Andrew will present, have questions. And then after that, we'll ask everybody to leave and we'll just have a private meeting with Andrew and the committee. Just a word before Andrew gets going. I think, was it 2019? We started working together. Andrew was still an undergrad, senior. And he did his MEng with me, sort of working on audiovisual representation, learning. And then a sort of branched out a little bit for his PhD, looked at different languages, representations for low resource languages, looked at speech, audiovisual speech recognition, and then with all this large language model craze, started looking at audio large language models. So he'll talk about some of all of these things today, I believe. He's been pretty prolific through the years. I think it's about 20 papers you've published while at MIT, and the stuff today will be the most recent work. So without further ado, I'll pass it over to you.
Thank you so much. All right. Hello, everyone. Thank you so much for coming to my PhD thesis defense. Let's get started. I'm going to begin by defining my title, Multimodal Multilingual Audio Understanding. So audio understanding is the ability to interpret information conveyed in audio. And in this thesis, we're interested in different types of audio, including speech, which is language transmitted by humans, sounds that can naturally occur in the environment through various physical processes, and also music. The multilingual aspect means the ability to recognize speech in many different languages, not just English or any particular language. And the multimodal aspect is the ability to integrate other perceptual modalities, including visuals and text. The reason we're interested in this is because visual information often co-occurs with audio in the natural world. And text is useful since we could enable a language-based interface with different models. In recent years, machine learning has really improved the field of audio understanding as a whole. And the main task of automatic speech recognition, or ASR, has significantly improved with much better performance. And nowadays, many different languages are supported by these models. And new audio models can even go beyond transcription towards audio question answering. However, they still face several challenges. For example, they struggle on lower resource languages or languages that we have less data for. They get worse in challenging acoustic scenarios such as noisy audio, and they don't understand vision by default and need better text-based reasoning. So in this thesis, I'm first going to present to you my work on comparing different audio encoders for multilingual ASR. And then I will show you how I made a audio-only ASR model into a multimodal model by integrating lip-based video into it. And finally, I'll show you how a project about fine-tuning audio LLMs with reinforcement learning for better audio question answering. Going to begin with some background about ASR. So traditional ASR usually needs a large amount of manually annotated speech data to get good performance. And by that, I mean we need speech audio paired with text transcripts where humans annotate what was spoken in the audio. And this can be both costly and time consuming. So self-supervised learning presents an alternative and needs much less labeled data. You essentially train a model on unlabeled data where you don't need human provided transcripts, and you train it on a proxy task such as mass reconstruction. And afterwards, you're able to fine tune this model on a smaller amount of labeled data and achieve good performance for ASR. One such model was Wave2Vec 2.0. So this model proposed to do pre-training on unlabeled speech audio where they would mask out certain parts of the audio and try to predict features corresponding to the masked portions. And through this process, they learned a good representation of the audio, and then they could fine tune it on a smaller amount of labeled data to achieve good performance. The multilingual version, XLS-R, was trained on audio in over 100 different languages and could learn a good general representation of different languages and then be fine-tuned for ASR in different languages besides English. However, there's a problem with self-supervised learning is that even though you can train on unlabeled data, you still need to fine tune separately for each task and language that you're interested in. So what if we could just pre-train directly for all the tasks and languages that we're interested in? That's exactly the approach that OpenAI Whisper took, where they collected labeled data from the internet and they trained directly for English ASR, multilingual ASR, and also speech translation, where you could have audio in different languages and translate the output into English. Because of this, Whisper became a very popular model and to this day remains very popular. So now that we've seen these two different approaches for ASR, I want to mention that they both have a challenge. And that challenge is that they were both only trained on around 100 spoken languages versus there are still several thousand spoken languages in the world. And both of these models omit them from their training. And many of these languages that they weren't trained on have over 1 million speakers, which makes them sufficiently popular enough to be of interest. So we wanted to find out which of these models would actually work better if we consider one of those unseen languages and we fine tune on it. So in this work, we consider these languages. Some of them are shown above. These models weren't trained on these languages, but we wanted to find out sort of which one would work better on them. Basically, we found 13 unseen languages on a data set called floors, which neither model was trained on, and also 18 seen languages to sort of gather more information about how the models compare with each other. And one main result from this work is that the number of hours seen per language and language family during the pre-training process is predictive of how the models will compare after fine-tuning on floors. And this is a little surprising because the models and the pre-training methods especially are very different, where one just requires mostly unlabeled data and the other one is training on labeled data. So this plot shows the pre-training distribution per language family for these two different models, Whisper and XLS-R. And language families are groups of languages that are considered to have a common ancestral language. Whisper was trained on more hours of languages in higher resource languages shown in blue. And XLSR has a different pre-training distribution and was trained on more data in other language families. Before I dive into the results, I'll mention that XLSR is usually fine-tuned with a linear layer decoder on top of a transformer encoder. And then Whisper follows a transformer encoder decoder design. And it's shown in bold are the model sizes and layers that we used. For the metrics, in this work, we use character error rate, which is defined over characters. And later on, we'll use word error rate as well. For both of these, lower is better. And in this particular work, we use character error rate because some of the languages don't have regular spacing. So characters are more appropriate. These are the results for the unseen languages. And just to remind you again, it's character error rate where lower is better. The XLSR models are shown in the greenish color versus the Whisper models are shown in the reddish colors. And you can see that across the board, XLSR is always doing better. And even the smallest model size outperforms the largest Whisper large size. And we attribute this to the fact that XLSR was trained on more hours of data in these lower resource language families. So besides the unseen languages, we also wanted to fine-tune on seen languages to gain more intuition about how these models would compare to each other. And this plot shows the result of applying Whisper off the shelf to these languages doing speech recognition and also fine-tuning Whisper and trying to see what the delta was. And we can see that for some of these languages, Whisper actually doesn't work very well out of the box, but when we fine-tune it, it gets significantly better performance. So we wanted to see, since we can fine-tune both XLSR and Whisper on seen languages, meaning languages that they were already trained on, we wanted to understand if the relative amount of pre-training data is predictive of their relative performance. So I will show you a plot where on the x-axis is the log ratio of XLSR's pre-training hours to Whisper's hours, and the y-axis is the log ratio of XLSR's performance to Whisper's performance. Let's take Ukrainian as an example. XLSR was pre-trained only on 72 hours of this language versus Whisper was pre-trained on 697 hours of this language. And we can compute the log ratio of their pre-training hours. And similarly, we can compute the log ratio of their character error rate, which is the performance after fine-tuning on this data set. If we take all of those data points and plot them, we get the following plot. And just to remind you, the x-axis is the log ratio of their pre-training hours, where on the left side, Whisper Small has been trained on more hours of these languages. And on the right side, XLS-R has been pre-trained on more hours of these languages. And vice versa, the y-axis is the log ratio of their character error rate. So the red line is the line of equal performance, because if they had the same character error rate, the ratio would be 1, and then the log of 1 is 0. So on this line, this represents the line of equal performance. Above this, Whisper Small is performing better, and below it, XLS-R is performing better. So we fit a trend line through this, and the R squared is decently high. So our main takeaway from this is that despite the very different pre-training strategies, meaning again, XLS-R was pre-trained on unlabeled data and Whisper was trained on labeled data, the number of hours seen per language is predictive of how the models perform. And finally, there's a slight bias here towards XLS-R, which is the larger model. This trend line is sort of below the line of equal performance. And that is intuitive because XLS-R actually has a larger model size compared to Whisper Small. One more takeaway from this work is that Whisper is a strong multilingual ASR model. And what's nice is that it already performs well zero shot, meaning without fine tuning, but it can get even better with fine tuning. And the rest of this results were published at Interspeech and are in our thesis. So next, I'll show you how I integrated lip-based video into ASR models to make it a multimodal model. ASR models are great, but they all have a problem that performance declines in noise and gets worse in challenging acoustic scenario. So shown in this plot are the performance of Whisper and other models. As the noise is increasing, the word error rate is also increasing, and recall that higher word error rate is worse. And at some point, they basically become unusable with a word error rate of 100%. Audio-visual speech recognition is actually a classic solution to this problem, where you train models not only on speech audio, but also on lip-based video. And the lip-based video is usually coming from videos like presentations or interviews on the internet. And audio-visual speech recognition is nice because in moderate noisy condition, you can get 2 to 3 times better performance than the audio-only model. One popular model is A.V. Hubert, and A.V. Hubert actually extended the audio-only self-supervised learning paradigm to the audio-visual learning scenario, where instead of just masking out audio inputs, you also mask out video inputs and perform a self-supervised training strategy to get a good representation. And then they fine-tuned it for the task of audio-visual speech recognition. One important thing for the rest of this work is that they actually train the model with something called modality dropout. In modality dropout, they entirely drop either the video or the audio modality entirely. And what that does is it enables the model to work with video-only inputs. The reason why it's useful is because we will want to combine the lip reading capabilities of this model with our audio-only speech recognition model. There's a natural problem that arises with audio and video data, that audio is much more easy to acquire than video data. Whisper was trained on 680,000 hours of audio data versus A.V. Hubert was only trained on 1.7 thousand hours, which is a huge difference in their training data sets. So because of that difference, it motivated us to ask the question of whether we could adapt Whisper to use a totally new modality of video information with only a small amount of label data to improve the noisy word error rate. So to be clear, our goal is that we want to combine Whisper, which is a strong audio-only speech recognition model, with the lip reading capabilities of A.V. Hubert. And also we want to use Whisper's strong multilingual decoder for English speech recognition and English to X speech translation. So now I'm going to go over the method, and we follow a 2-stage approach, where in the first stage, we want to make Whisper more noise robust. In this stage, we fine-tune the audio-only Whisper while adding noise to the audio. And the noise includes different types, including speech, music, and babble sounds. And in this stage, we fine-tune all of the parameters. In the second stage, this is where we inject the visual features into Whisper. Here we freeze Whisper, add new layers into the model, into the decoder, which are attending to A.V. Hubert's features, and then train the model on audio-visual inputs. The way we do this is with gated cross-attention. This is pretty similar to a regular cross-attention to the visual features from Whisper's decoder. However, we also have this gating functionality. In the beginning, this is initialized to 0 since these alphas are 0. So we're essentially have just a bypass layer, and the model ignores the visual modalities. Over time, the model learns to start attending or pay attention to the visual features by adjusting these alphas, which is nice because it makes a gradual transition from an audio-only model to an audio-visual model. We also fine-tuned the model for English to X speech translation, where we have English audio with English text, of course, but we also have the translations into 6 different languages. And these are the supported languages. This is a schematic of the overall architecture. In the beginning, in the center of it, we have Whisper's audio encoder decoder. Then we have AV Hubert, which is taking in the lip-based video as input. We have Whisper's decoder, and here we're inserting the gated cross-attention layers into each block of Whisper's decoder. And finally, we have the English to X translation tokens, and these are used to train the model to output text in different languages. For the experiments, as I mentioned before, we use word error rate, where lower is better. For the translation, we use the blue score metric and here higher is better, so it's flipped. For the noisy testing setup, we first evaluate on the clean audio, which is just the original audio from the test set, and then we add noise to the audio for the noisy setup. All right, so these are the main results for English transcription. And just remember that it's word error rate, so lower is better. Without any fine tuning, Whisper does already pretty well on this data set, getting a respectable word error rate of around 2%. However, when we add noise to the audio, the word error rate gets much worse. So after we fine tune Whisper, it improves the word error rate both in the clean scenario and in the noisy scenario. And the main result is that the audio-visual Whisper Flamingo maintains the performance in the clean scenario. And the main result is that it further improves the performance in the noisy scenario. So it shows the advantage of using the lip-based video. Finally, compared to our lip reading backbone, AV Hubert, that model can also be applied in the AV scenario. But we actually get better performance in both the clean and the noisy scenario, which shows the advantage of using that model as a lip reading capability into Whisper, since we get better performance. To verify the noise robustness of our audio-visual model, in different types of noise, we evaluated on 6 different types of noise using 5 different signal-to-noise ratios, which varies the intensity of the noise. In this plot, we show the different noise types averaged over the 5 signal-to-noise ratios. In red is the original Whisper zero-shot model without any fine-tuning. Then the blue model is our audio-only Whisper, fine-tuned from stage 1 on noisy audio. And then we have Whisper Flamingo, which is our proposed method using both audio and visual information. And you can see that the bars in green are the lowest, and no matter the type of noise, our audio-visual model is doing the best. Finally, we have the results for the English to X translation, where we have English audio and video and text translation output in 6 different languages. First of all, we have Whisper audio only, which we fine-tuned for this task. And now we have blue score, so higher is better. In the noisy scenario, the performance drops similar to the transcription. The audio-visual model maintains the performance in the clean scenario and gets better performance in the noisy setup. Finally, compared to the previous state-of-the-art bilingual AV Hubert, we get better performance in the clean scenario and slightly worse in the noisy. However, the previous state-of-the-art fine-tuned separately for each language and use a separate model for each target language. So basically, they have 6 different models that we're comparing against. Meanwhile, our model was only trained once for all different languages, so it's more scalable. Okay, so now I'm going to show a demo video of Whisper Flamingo. And here we're going to have both the audio and video as input to the model, and the model will make a prediction of what the person is saying. So I'd invite you also to try to predict what the person is saying.
It's using past experience based on similar situations to try to make meaning. It's using past experience based on similar situations to try to make meaning.
So our model, despite all of the background noise, it only got 1 word wrong. And also at the end was a demo of the translation output. Okay, awesome. So far we only used English videos as input, but Whisper, as I mentioned, was trained on audio in 100 languages. So we wanted to find out whether we could train a multilingual version of Whisper Flamingo on videos in different languages. To do this, we propose Whisper Flamingo. The M stands for multilingual. We're going to train it on a data set of videos in 9 different languages. And the goal is that the audio-visual model should be better in noise for all languages, meaning every time we have a language and we add the video, the performance in noise should get better. But the default setup actually didn't work well for the non-English languages. So our solution to this is decoder modality dropout. In decoder modality dropout, we randomly replace the inputs to the decoder's audio and visual cross-attention layers with 0 vectors. And the advantage of this is that the encoders get to stay specialized on their specific modalities while the decoder learns better multimodal integration. This is a picture of Whisper Flamingo in the default training setup, which is no dropout. And we denote this by probability of AV, audio-visual training. You can see that there's a cross-attention going from both the visual features to the decoder and also the audio features to the decoder. When we enable the decoder modality dropout, we denote video-only training by PV. And here you can see we actually zero out the cross-attention to the audio features. And vice versa, when we have probability of audio-only training, we zero out the cross-attention to the video features. We did a sweep over the probabilities, and we found that the optimal setting was to train 50% of the time on audiovisual inputs and 50% of the time on video-only inputs. And the full sweep of the probabilities are in our thesis. These are the different languages that we use. Besides English, there are 4 languages with over 100 hours of data, which is a pretty good amount of data for this task. There's also 4 languages with less than 100 hours. And it's actually more challenging to learn good lip reading when you have less than 100 hours. These are the results for the clean setup, where we have the 9 different languages, and we have our model shown in yellow versus the previous state of art in blue. So even though our model has a slightly smaller parameter size, 1.4 billion versus 2 billion, we're getting better performance across the board thanks to Whisper's extensive pre-training on many of these languages. And also we're able to get good performance on English. So we can enable good multilingual performance while maintaining English performance. For the noise robust experiments, we specifically focused on the results without English to demonstrate the multilingual effectiveness. So here we repeat the noisy experiments, except we focus and average over these 4 languages without English. So these are the results. Again, for each different noise type, we averaged over 4 languages and 5 different signal to noise ratios. And we can see again that the audio-visual model shown in green is always doing the best, no matter the different types of noise. However, the gap between the green and the blue bars isn't that large. So it's not as giving as much boost as the English scenario. Okay, now I'm going to show a demo of the multilingual capabilities. So there will be a video of 5 different people speaking all together, and they're speaking in different languages. Then we can individually feed each person's video into the model and get a output specifically for that person while feeding in the mixture audio.
Cuando tenía 5 años y empezaba a leer, mi querido abuelo Carlos Felipe me regaló un libro de aventuras.
Okay, so that was the result for the first speaker. You can see the model picked up many of the words correctly, but it's not quite as perfect as for the English scenario. So for the multilingual setup, there's definitely more room for improvement. I think the thing which is going to give the biggest delta in the future is more data collection, actually. So that concludes this section of my thesis. To wrap it up, Whisper Flamingo combines the strengths of Whisper and AV Hubert using gated cross-attention. And we were able to get a new state of art for multilingual audiovisual speech recognition in 9 different languages. And the nice thing about this is that our method is general and could work with better encoders in the future. And this work was published at Interspeech and Signal Processing Letters. In the last section of my thesis, I'm going to describe the fine-tuning of audio LMs with reinforcement learning for better audio question answering. So Whisper is a great model for ASR, but it doesn't support open-ended questions about audio. So if you're wondering anything else about the speech you're listening to, besides just what was spoken, it doesn't support that. A naive solution that actually works quite well in practice is to combine Whisper's audio encoder with modern text-based LLMs. That's exactly the approach that Qwen2 Audio, as well as other audio large language models take. In particular, Qwen2 Audio starts off with the Qwen LM and adds Whisper's encoder for audio understanding. This process in this figure shows the overall process of integrating the audio encoder into Qwen LM, where they begin with different tasks such as ASR and captioning. Then they fine tune on chat data. And finally, they have a stage for reinforcement learning, where they either try to get better alignment with human preferences, or they try to get better performance on advanced tasks. And in this work, we're going to focus specifically on the last portion, which is the sort of the reinforcement learning stage. For our audio LMs, we're going to need a good benchmark. And here we're going to use the MMAU benchmark, which contains questions about audio in different categories, such as sound, speech, and music. And the questions for speech go beyond transcription, can ask questions about word order or how many times a word appeared. The inputs to the model will be the text question and the answer choices. And in addition to that, of course, the input audio. The model will then have to output the text answer of the correct answer. And because of this fixed choice answer property, where we know which answer is correct in advance, it's relatively straightforward to verify that the model got the answer correctly or not. And it's also easy to compare different LLMs against each other, since we can compute a classification score and use that to compare against different models. One work that inspired us was R1AQA. And what they did was they fine-tuned Qwen2 Audio with reinforcement learning. Specifically, they used group relative policy optimization, or GRPO, from DeepSeek R1. And in this method, you use verifiable rewards. Verifiable rewards is pretty straightforward. It means that during the training process, we are training the model with types of problems that we can easily verify if it got the question answer, if it answered the question correctly or not. And here, for example, we can give it a reward for getting the correct answer and also for getting the correct format, which helps with sort of parsing the answer during the evaluation. This type of audio question answering works great with this methodology because we know which answer is correct, so we can give the model a reward during training if it got the correct answer. This plot summarizes the results from R1AQA, where on the y-axis we have the average accuracy on MMAU. It's percentage score, so higher is better. And they started off with the base model, which got around 50%. And they compared with standard supervised fine-tuning and the reinforcement learning-based fine-tuning. And as you can see, the reinforcement learning-based fine-tuning got significantly better performance than the standard setup for fine-tuning. When we saw those results, we wanted to understand why were the gains so large for the GRPO-based fine-tuning. Also, will the improvement generalize to other models? Most importantly, is this improvement actually improving the audio perception capabilities or just improving the core text LM understanding? And finally, since we have a limited amount of training data for this particular task, could we generate synthetic data to further improve the performance? So now I'm going to go over the method. As I mentioned, the rewards are verifiable. So we have a correctness reward, which is 1 if the answer is correct and otherwise 0, pretty standard. We also have a format reward, which is just 1 if the answer is within these answer tags and otherwise 0. And as I mentioned, this helps extract the answer during the evaluation. For the fine-tuning setup, we need a data set with sort of audio and these fixed choice question answers. Fortunately, there's already a data set out there called AVQA. It's a subset of VGG sound, which is designed to have high correspondence between the video and the audio. And here we only use the audio files. And it features 40,000 question and answer pairs, which were written by human annotators. In terms of another model we use the next generation Qwen Omni model, which features, in addition to the audio input, it can also handle videos input and output TTS. But for the sake of comparison with Qwen Audio, we just focus on the audio encoder and the LLM component. This chart shows our results when we compare the next generation Qwen Omni with the previous Qwen2 Audio. And looking at the base model, it already outperformed Qwen Audio, which was fine-tuned with reinforcement learning. When we applied the same reinforcement learning strategy to Qwen Omni, we were able to get a boost in improvement. But this improvement is not as large as it was for Quen Audio. So we wanted to understand, why was Quen Audio improving far more greater than Quen Omni? And also, again, whether the improvements are audio driven or just improving the core text LLM. To do this, we test the models without audio. During inference, we withhold the audio from the prompt, and we took this a step further and we fine-tuned the models without any audio, meaning text-only mode. And you may ask, how is it possible that these models can answer questions without the audio, given that that was the whole point of the benchmark? Well, if you look closer at the questions, there are some questions which have leakage from the question to the answer. For example, here's a question. It says, based on the given audio, identify the source of the crowing. If you listen to the audio, you can hear that there's a rooster crowing in it, but also any reasonable LLM would know that of the following answer choices, a rooster is the one that makes the crowing sound. So that's how the models are able to answer some of the questions, even without listening to the audio. So this table will summarize our results in this investigation, where we have Quen Audio first and then Quen Omni. And we start off with the base models, and we test them in the standard setup with audio and then without any audio, so text-only inference. And Quen Audio is doing something reasonable. It's getting close to chance performance, 30%, where chance is around 25%. Meanwhile, Quen Omni is actually getting close to double chance performance. It can answer already half of the questions in the data set without any audio, just looking at the text questions and answers. Meanwhile, after we fine-tune the model with audio, we again tested the performance without audio. And we found that actually Quen Audio improves significantly in this case versus Quen Omni doesn't improve significantly. So the picture is starting to make a little bit more sense. Quen Audio started off with a weaker text LLM for this task versus Quen Omni started off with a much stronger text LLM for this task. And with the fine-tuning process, it seems to impact the text understanding a lot, which translates over to the audio inference numbers. To take it a step further, as I mentioned, we also fine-tuned without any audio. So the first thing we did is we took the same data set and we just dropped the audio and fine-tuned it on the text Q&A without the audio. And what we found was interesting. Basically, the performance, you also got a significant boost in performance in both evaluation setups for Quen Audio, but not Quen Omni. So again, it shows that Quen Audio is sort of starting off with a weaker text LLM, and it's improving thanks to the text-based fine-tuning. Finally, we took a data set, even without any audio in it, just a text Q&A data set called ArcEasy. And we fine-tuned on this data set and found that by fine-tuning on it, we could nearly match the performance of fine-tuning with audio, which is a bit surprising. So why does text-only fine-tuning improve the performance? We think it's a combination of two reasons. The first is we think it helps the text-based understanding. As I mentioned, there is some sort of understanding that could be improved, such as like if the rooster is crowing or what animal makes the rooster crowing sound. It is also helping with the model output formatting. And what I mean by that is the evaluation script is easy, but pretty naive, or pretty strict, rather. It expects an exact string match of the correct answer without any exact matches of the incorrect answers. So for the base model, you might tell it to answer the following question and give me the answer directly. It might ignore your instructions. It might first want to compare all the different options and so forth. And that might be hard to parse by the evaluation script, which could mark that answer incorrectly, even though its final answer is correct. So overall, you do need audio to fine-tune your audio LLM. The performance with the audio-based fine-tuning was the best, but we found that much of the improvement was text-driven. And surprisingly, fine-tuning on text-only QA was surprisingly effective. Finally, we wanted to see if we could generate synthetic data to train the model. And the reason we need synthetic data is because we actually don't have a lot of audio data which has labels in the following format. We have a lot of ASR data and captioning data, but not too many question answering data sets in the following format. So to generate more synthetic data, we followed a semi-automatic approach where we first collected captions of audio from a previous audio LLM, actually Quen Audio. And then we prompted ChatGPT, given these text captions, to generate question answers in the following format. We generated two synthetic data sets. The first is AVQA GPT. So here we use the same 40,000 audio files as AVQA, but now we have synthetic question answers versus VGG Sound GPT, we scaled up to the rest of the audio files to get even more training data. The main difference I want to point out between the human annotated data and the synthetic data is that actually the synthetic data is more diverse and has more unique questions and answers. If you look at the human annotated data, there's only 775 unique questions and out of 40,000 questions. And I think it's because the annotators must have been provided with like a list of questions, or they must have found it difficult to come up with new questions on the spot. So that is one advantage of using ChatGPT to write your questions for you. This plot shows the results of fine-tuning on the human annotated data versus our synthetic version, which uses the same audio files, just with questions written by ChatGPT. And we can see that actually we're getting slightly better performance by fine-tuning on the synthetic data than the human annotated data. And that sort of verifies the effectiveness of this process that we followed. When we scaled it up to more synthetic data, fortunately, we got even better performance. So now I'll show you the main results on MMAU. At the time of publication, we compared with all the latest open source and closed source models. So basically, the top of this table shows all the previous models, and the bottom shows our results. And when we fine-tune on AVQA, we could already get better average performance than pretty much all of the previous models. By using the synthetic data, we obtained the new state-of-the-art models across the different types of audio. We also evaluated on the test full set. So this split has 9,000 audios, and the answers are actually hidden behind a private leaderboard, which makes it harder to overfit to these samples. And similarly, we got the state-of-the-art performance here. Using the synthetic data did give a boost, but it wasn't as large as on the test mini set. To wrap this section up, GRPO is boosting the audio LM accuracy on MMAU, but much of the gains are from the improvement in the text understanding. And surprisingly, the text-only fine-tuning was useful for improving the performance. Our synthetic QA generation pipeline produced the best models. And these results were published at ASRU. I want to spend a minute now discussing some ideas for future research. The next generation of speech models are going to go beyond simple transcription and more towards models that can not only understand what you're saying, but also how to reply and carry a conversation. One example of an initial system is proposed here, Moshi. And I think the multilingual aspect will be very interesting. In the future, you might be able to have a conversation with such a system in many different languages. And also it could support code switching, where you're either using multiple languages simultaneously, or you speak in one language and the system responds in another language. I think interaction will also enable better audio-only understanding and unlock better understanding of other modalities as well. So the current benchmarks sort of represent single shot scenarios where they listen to audio and then are expected to provide an answer. But real audio understanding involves listening, acting, and re-listening. For example, imagine your car breaks down and you take your car to a mechanic. And what they do is they might listen to the engine from different points of views. They might probe some parts, replace something, and listen to it again. And similarly, I think in the future, we could have audio LLMs running on our phone. If we get stuck on the side of the road, we might be able to pull it out and have it help us at least understand what is wrong with our car so that we can get better help. To unlock this kind of behavior, I think we'll need new platforms besides the current benchmarks, and the platforms are open to research. This could include 3D robotic environments, web interfaces, and music composition software. But importantly, I think the audio LLMs will need new APIs, such as the ability to play audio, to seek audio, filter, and generate edits. Great. So now I want to go into some acknowledgements. I first want to thank my advisor, Jim, for being a great advisor and very supportive during my PhD journey. I want to thank him for believing in me and trusting in me to carry out this research. I want to thank my committee members, Professor Bill and Professor Yoon, for being a part of this very important part of my PhD journey and for providing expert advice from another point of view. During my PhD, I had the chance to work with many wonderful advisors and collaborators through the Sight and Sound Project, MIT IBM Sight and Sound Project. And I want to thank all of the people here, as well as maybe a couple others whose photos I wasn't able to get. But I thank everyone for helping me to become a better researcher. As Jim mentioned, I joined the project in 2019 when I was just a fresh graduating undergrad, very excited to do research, but didn't quite have the skills yet. So I'm grateful for them for walking with me through the journey and helping me to become a better researcher. During my PhD, I also had the chance to do a couple of internships, and I want to thank my mentors specifically for devoting a lot of their personal time to welcoming me and helping me to become a better researcher in new environments. I also want to thank all of the members of SLS, through whom throughout the years I've had a wonderful experience doing research with. I've learned a lot from them, with them, and I always felt like I was coming to do research with my friends. So thank you so much. I'm happy to take questions now. Yes, I will. And also I will show something in the appendix about that, if I can find it. Okay. So the question was, does for the GRPO section, whether the model has any reasoning output? And I think that's a good question because usually GRPO is combined with reasoning, where we want the model to sort of output its thinking process. And in this work, actually, no. In our final output, our model just directly outputs the answer and skips any reasoning. And one reason for that is that we tried incorporating some thinking process during the training, and it actually resulted in lower performance. So even though the model might put some thoughts about how to get to a better answer, the performance actually decreased for us. So that's why we didn't include it at the end. But I think that there's actually room for improvement in future work. There's a concurrent work called Audio Reasoner, where they want the model to output lots of these reasoning chains in its output process. And what they do is that they just train directly, supervised fine-tuning to output these reasoning chains. So I think it's promising in the future to combine both. First, do supervised fine-tuning to help give the model the desired structure of the reasoning, and then to do the GRPO, where it sort of can explore and learn how to like maybe put some other kinds of reasoning that would be helpful. Yeah, thank you. Awesome, thank you for the question. So just to repeat the question and make sure everybody here heard the question, Quan Wei's question was, do I have any thoughts on training models, ASR models that can support multiple languages at the same time? So the example would be, suppose I'm saying a sentence and then I start mixing in words from another language. So this situation is usually called code switching. And it's challenging to get a good model because the problem is we have limited data in this scenario. It always ties back to what data we have available. There is some data on the internet that is already naturally code switched. For example, usually code switching is done with English because people will adopt English words to describe some concept in their own foreign language. And lots of that data is already online. So that's sort of the easiest case. But there are more challenging cases where you have non-English languages and people are mixing two different languages. And what I've noticed from other speech research papers is that they will actually try to synthesize code switched audio. They will take this audio file and this audio file, they will concatenate them and take their transcripts and concatenate them. And that's sort of like a naive way to enable some of this initial behavior. But I think that's an active area of research as well. Yeah, so the question is, so I showed this results on unseen languages, and I said that XLS-R was trained on more hours of data in similar language families. And you asked me like, how similar are those other languages? Yeah, that's sort of hard to answer because I'm not a linguist and I don't understand fully the similarities between different languages. So language family was sort of my naive way of just like grouping languages together and giving an explanation. But yeah, it would be helpful to have more research and consult with like linguists and maybe get more of these differences, and also to check also what type of output unit it uses. Does it use Latin script? Does it use like its own language specific script? I think this will also impact the results. Thank you so much for coming, everyone. So now I have to spend some time with my committee.
Yeah.
So.
And for those who want to hang around, we'll have a get together on the 4th floor after the.
Thank you. Let's see, something in the chat. Okay. All right. Thank you everyone on the Zoom for joining. That concludes the private public section.